Ultrasound and its applications. All physical phenomena such as fire, rain, wind, earthquake, and volcano produces unique sounds. For humans, hearing is limited to frequencies ranging between 20 Hz and 20 kHz. However, the upper limit generally decreases with age. Different species have a different range of hearing. For example, dogs can hear the sounds with frequencies up to 25 kHz. Sound with frequencies smaller than 20 Hz is known as infrasound or infrasonic wave. If we could hear infrasound, we would hear the vibrations of a pendulum just as we hear vibrations of the wings of a bee. Rhinoceroses communicate using infrasound of frequency as low as 5 Hz. Elephants also produce sound in the infrasound range. It is observed that some animals get disturbed before earthquakes. Do you know why? Earthquakes produce low-frequency infrasound waves before the main shock begins, which possibly alerts the animals. Sound with frequencies higher than 20 kHz is known as ultrasound or ultrasonic wave. Ultrasound is produced by bats, dolphins, whales, and porpoises. These animals use ultrasound waves to find their distance from an object using the mechanism of echoes. They emit ultrasound squeaks that bounce back as echoes from the surfaces in front of them. The time between a squeak and its echo can make them judge the distance of the obstacle or prey in front of them. They can also judge whether the thing is an obstacle or a prey, whether it is moving or stationary, its size, etc. In other words, they use ultrasound waves as their third eye. Some of the moths can also hear ultrasounds. These moths can hear the high-frequency squeaks of the bat and know if a bat is flying nearby and are able to escape the capture. Rats also produce ultrasounds. Ultrasound waves can travel quite freely in solids and liquids as compared to gases. Because of their high frequency, these waves also have some special properties that an audible sound does not have. Normally, ultrasound waves exist in solids, liquids, and gases. There are two types of ultrasound waves, that is, longitudinal waves or transverse waves. Similar to the sound waves, ultrasound wave also carries energy with it. This energy is transferred to the medium through which the wave is passing. A region of compression and an adjacent region of rarefaction constitute one cycle of an ultrasound wave. An ultrasound wave cycle can be represented as a graph of change in the pressure or particle density of the medium versus distance in the direction of the ultrasound wave. The maximum height of the wave cycle, that is, the maximum value of the pressure or the density on either side of the normal value, is the amplitude of the ultrasound wave. The distance covered by one cycle is the wavelength of the ultrasound wave. It is the distance between the centers of two consecutive compressions or two consecutive rarefactions. Wavelength is a useful parameter in ultrasound waves. In ultrasonic detection of a small object, the smallest size that can clearly be detected must be larger than half of the wavelength at the operating frequency. If the critical size of an object to be detected is known, such prior information on size is helpful for selecting an appropriate frequency for measurements. The number of cycles introduced into the medium each second is referred to as the frequency of the ultrasound wave. It tells us how frequently a wave is passing through a point. In other words, it is the number of the compressions or rarefactions that are crossing the given point in 1 second, expressed in units of hertz, kilohertz or megahertz. An ultrasound wave can be made very powerful due to its high frequency. The energy of a wave depends on several factors such as amplitude of the wave and its frequency. For example, when we shout at loudspeaker, we produce power of about 0.001 watt. However, if a source vibrates with the same amplitude as the sound we produce, but at 1000 kHz, then it would produce 1000 watts of power. The high power of ultrasound waves is used in industry and medicine to break and cut objects. Ultrasound waves are able to travel along well-defined straight paths even in the presence of an obstacle. This means that they do not bend at the edges of the obstacle. When a low-frequency sound wave strikes an obstacle, it easily bends round the corners and spreads in all directions. For example, if we keep a board between our face and source of the sound, we can still hear the sound. This is because the sound waves bend at the corners of the board and reach to our ears. Having high frequencies, this bending phenomenon is quite insignificant in ultrasound waves, just like light. In this respect, ultrasound waves move along straight line. Thereby, ultrasound waves are used for imaging objects. The benefit over light is that ultrasound waves can travel through opaque materials also where light cannot travel. They can be transmitted over long distance without any appreciable loss of energy. Speed of the ultrasound wave is the product of the frequency and the wavelength. In general, the speed of the ultrasound wave is determined by the compressibility of the medium. A medium with high compressibility has low ultrasound speed and vice versa. Hence, the speed is relatively low in gases, intermediate in liquids such as blood, and largest in solids such as bone. Because of its properties, ultrasound waves are used extensively in industries and for medical purposes. Metallic components are used in buildings and machines. If there are cracks or holes inside the metal used, the strength of the structure or the component is reduced significantly. Sometimes such defects are not visible from outside. Ultrasound waves can be used to detect flaws in metal blocks or sheets without damaging them. For example, ultrasound waves are passed through such metallic objects. If there is no crack or cavity in its path, it goes through the object, and a detector placed on the other side detects the transmitted wave. Any defect present in the path of the wave reflects the wave, and the region having defect does not transmit any wave. When this happens, we know that the object has a defect inside. We generally use a hammer and a steel punch to make holes in metal plates, plastic sheets, or other solid materials. Such holes can also be made using a metallic rod called horn, through which ultrasound vibrations are produced. Similar to a hammer, it hammers the plate about 100,000 times per second. The shape of the hole is the same as that of the tip of the horn. Therefore, shape of the tip can be designed as per the requirement of the application. Ultrasound cutting and drilling are very effective for brittle materials such as glass, for which ordinary methods of cutting might not succeed. Ultrasonic technology is also used to find the level of a liquid in a metal tank without opening it. Ultrasound waves are used for mixing immiscible liquids like water and oil into a homogeneous stable substance. This technique is also used for making photographic film. For cleaning small parts such as the ones used in watches, electronic components, odd-shaped parts such as spiral tube and parts located in hard-to-reach places, normal methods of cleaning is inconvenient and sometimes impossible. Such objects are cleaned by using ultrasound vibrations. For this, such objects are placed in a cleaning solution and the ultrasound waves are allowed to pass through the solution. Due to these waves, high-frequency vibrations are set in the solution that knocks off all the dirt and grease particles from the object. Ultrasound wave is a powerful tool for imaging human organs. Ultrasound has a very high penetrating power and it can penetrate the human body and its different tissues such as bones, muscles, fats, etc. Three-dimensional images of internal organs of the human body such as liver, gallbladder, uterus, kidney, etc. can be obtained by using ultrasound waves. Ultrasound scanner is an instrument that uses ultrasound waves for getting images of the organs. It helps a doctor to detect abnormalities such as stones in the gallbladder and kidney or tumors in different organs. In this technique, a source of ultrasound is placed above the organ which is to be investigated. The ultrasound produced by the source penetrates through the body and gets reflected from the organs. Ultrasound waves are sent from different angles and all the reflected waves are gathered by a receiver that converts them into electrical signals that are used to generate images of the organ. The length, breadth and depth of the different organs can also be measured. These images are displayed on a monitor. Even a photograph of the organ can be obtained. This technique is called ultrasonography. Ultrasonography is safer than X-ray imaging technique as the ultrasound waves do not damage the delicate tissues of the body. That is why ultrasound scans are used to monitor the development of the baby inside the mother's womb. Ultrasound is also used to break small stones that are formed in the kidneys into fine grains, and these grains are flushed out with the urine. This method has eliminated the necessity of surgery. The lens of the eye is made up of a clear gel surrounded by a transparent membrane called lens capsule. With old age, this gel may become cloudy and hard. Light passing through it becomes diffused, causing blurry vision. Ultrasound waves can cause molecules of materials to vibrate vigorously, thereby it is able to break certain materials into tiny pieces. When the ultrasound waves is passed through the hardened gel, it breaks the gel into tiny pieces, and a plastic lens is placed in capsule to restore the vision. This technique is commonly used for cataract removal. Ultrasound waves are used in the treatment of muscular pain because they produce a relaxing massage. It is also used for treatment of arthritis which occurs due to inflammation of joints. Ultrasound is also used to measure the depth of seas or oceans and to locate underwater objects like shoals of fish, submarines, shipwrecks, sea rocks, and icebergs hidden in the sea. From the observation center on the board of a ship, ultrasound waves of high frequencies are sent in all directions under the water. These waves travel in straight lines till they hit an object such as a submarine or the seabed. The reflected waves are received back at the observation center. The direction from which a reflected wave comes to the observation center tells the direction in which the object is located. By knowing the time between sending the ultrasound wave and receiving its echo, and the speed of sound in sea water, the distance of the object from the observation center can be measured. The longer the delay between the transmitted and reflected pulses, the deeper the object is. Reflections from various angles can be used to determine the shape and size of the object. This method of finding distances is also called echo ranging method. The device used in this method is called sonar, that stands for sonographic navigation ranging. Human ear. Our ears are extraordinary organs. They pick up all the types of sounds around us and then translate this information into a form that our brain can understand. Let's discuss different parts of the human ear. It has three main sections: the outer ear, the middle ear, and the inner ear. Outer ear. The outer ear or external ear is a visible portion of the ear. It collects and guides sound waves into the middle ear. Middle ear. It is an air-filled cavity and consists of the following parts: the eardrum, also known as tympanic membrane. It is a thin membrane that acts as a partition between the outer ear and the middle ear. Three small bones located next to the eardrum: malleus or hammer, incus or anvil, and stapes or stirrup. The oval window. It is a membrane-covered opening which leads from the middle ear to the vestibule of the inner ear. Inner ear, as the name suggests, is the innermost portion of the ear. It is filled with a water-like substance and comprises both hearing and balancing organs. The eustachian tube is a tube that connects the middle ear to the throat. It equalizes air pressure on both sides of the eardrum, preventing it from damage. Cochlea. It is a coiled tube filled with a fluid having receptors to detect vibrations. Auditory nerve. The electrical impulses generated by nerve cells are then passed on to the brain. Three semicircular canals are situated at right angles to each other. These fluid-filled loops are attached to the cochlea and help in maintaining the balance. Let us understand how we hear sound. The source of sound produces a train of compressions and rarefactions in the air. These waves enter the outer ear and travel through the ear canal to the middle ear. Moment the air near the eardrum is compressed, it pushes the eardrum inwards, and as it is rarefied, it moves the eardrum outwards. In this way, the waves cause the eardrum to vibrate. The eardrum passes these vibrations on to the three tiny bones present in our ear, and that make each of the interconnected bone to vibrate. The interconnected bones behave like a lever that increases the displacement during vibration. So, the displacements of the stirrup become manifold that of the eardrum. Thereby, the amplitude of the wave gets amplified. From the smallest bone stirrup, the vibrations pass into the inner ear. The vibrations travel into the cochlea and convert these vibrations into nerve impulses. Auditory nerve carries these nerve impulses to the brain that interprets this information as a specific sound. In general, sound means those vibrations composed of frequencies capable of being detected by ears. It is the ear that differentiates the sound of different types. For example, a violin and a flute may both be played at the same time in an orchestra. Both sounds travel through the same medium and arrive at our ear at the same time. Both sounds travel at the same speed irrespective of the source, but the sounds are received by our ear are different. This is due to the different characteristics associated with the sound. When we stand close to an audio system, the sound produced by it appears very loud, but the same sound appears faint when we stand far away from the audio system. It means sound as heard by us depends on many factors such as amplitude and frequency of the sound, etc. We know that men's voices are grave,
7, 6, 5, 4, 3, 2, 1.
while the women's voices are shrill.
6, 7, 8, 9, 10.
How a brain interprets the frequency of an emitted sound is called the pitch. The faster the vibration of the source, the higher is the frequency and the higher is the pitch. If we plot the graph of sounds, it can be noticed that the sound of high pitch has more number of vibrations than that of the sound of low pitch. Thus, a high-pitched sound corresponds to more number of compressions and rarefactions passing a fixed point in unit time. Objects of different sizes and conditions vibrate at different frequencies to produce sounds of different pitch. Let us see the examples of sounds of low pitch and high pitch. Noise of the engine of a vehicle is the example of sound of low pitch. Whereas the chirping of a bird is the example of high pitch. Sound produced by a musical instrument is also an example of high pitch. In general, pitch is used to distinguish between shrill and grave sounds. Let us see an activity to differentiate between the sounds of different frequencies. Take few bottles of same type filled with water up to different length. Now, blow air from the mouth of each bottle. Here, it can be noticed that the sound from the bottle filled with water up to maximum level produces sound of highest pitch, and the sound from the bottle filled with water up to minimum level produces sound of lowest pitch. It is clear that men have low-pitched voices
10, 9, 8, 7, 6, 5.
and women have higher-pitched voices.
2, 3, 4, 5, 6, 7.
Our ears are also very good detectors of energy. A disco produces sound energy at a rate of about 40 watt, and we find this very noisy. If we have to light a disco with one electric bulb of 40 watt, everyone would complain that it is too dark. If we strike a drum lightly, we hear a soft sound because we produce a sound wave of less energy or small amplitude. If we hit the drum hard, we hear a loud sound as we have produced a sound wave of more energy or large amplitude. If we plot the graph of sounds, it can be noticed that loud sound has higher amplitude than that of soft sound. We know that the magnitude of maximum disturbance in the medium on either side of the mean value is called amplitude of the wave. Though it is hard to show amplitude in longitudinal waves, but sound waves definitely have amplitude. The louder the sound, the greater the tendency of the air molecules to be in high points of the waves, rather than in between the waves. Loud sounds produce waves of higher amplitude. The loudness or softness of sound is determined basically by its amplitude. The amplitude of the sound wave depends upon the force with which an object is made to vibrate. A loud sound can travel a larger distance as it is associated with higher energy. As the sound wave propagates, its associated energy spreads out from its source over a progressively larger area. As a result, the energy of the layers of air largely decreases with distance. Thereby, when sound moves away from the source, its amplitude as well as its loudness decreases. That is why sound produced through a loudspeaker, being loud, can travel a larger distance as compared to the sound being produced by a human being. Same can be noticed with the sound produced by a lion and by a bird. The sound of the lion is of very high amplitude than that of the bird. Generally, we use the terms loudness and intensity interchangeably, but they are not the same. Intensity of sound is the amount of sound energy passing each second through unit area. In other words, it is the power per unit area, and loudness is a measure of the response of the ear to the sound. Even when two sounds are of equal intensity, we may hear one as louder than the other. This is simply because our ear detects it better. The loudness of sound is measured in decibels. However, This is not an absolute scale of the measurement. Sometimes, decibel is defined as the smallest change in volume that can be clearly perceived by a human ear. The lowest threshold of human hearing is of 0 decibels.
Hello.
It is a condition of near total silence. A sound of 10 decibels is 10 times more powerful than the 0 decibel sound.
Hello.
A sound of 20 decibels is 100 times more powerful.
Hello.
Whereas a sound of 30 decibels is 1000 times more powerful than that of 0 decibel sound.
Hello.
Let us see some examples of the sound of different loudness. Sound of leaves is very soft as it has a sound of very low amplitude with a loudness of 20 decibels. Normal sound of a human being is also a soft sound as it has low amplitude with loudness of 60 decibels. Sound of an engine of a vehicle is the example of sound of high amplitude with loudness in between 70 to 90 decibels. Sound of lightning is the example of sound of very high amplitude with loudness in between 100 to 110 decibels. The same sound will not be perceived in the same manner by all individuals. Age is one factor that affects the human ear's response to sound. A sound of single frequency is called a tone. The sound which is produced due to a mixture of several frequencies is called a note. And is pleasant to listen to, such as the sound produced by musical instruments. The quality or timbre of sound is another characteristic which enables our ears to distinguish one sound from another having the same pitch and loudness. For example, a note of frequency 256 Hz, this note can be played on a piano or a violin. Somebody listening to the two different sounds would recognize straight away whether the note is played on the piano or violin. The quality of the two notes is different. The quality of a note depends on the shape of its waveform. Although two notes may have the same frequency and amplitude, if their waveforms are of a different shape, our ears detect the difference in sound. The sound which is more pleasant is said to be of a rich quality. Music is pleasant to hear and is of rich quality. Sound which is of low quality is called noise. Noise is unpleasant to the ear. Guess which sound has a higher pitch? Guitar or drum beat? Yes, guitar has a sound of higher pitch.